Hello everyone, welcome to part 19 of my video series on moment generating function. This is one of those core concepts which are not discussed a lot in the community, but it is at the core of the probability distributions. So without further ado, let's dive in. So first of all, let's discuss some properties of the probability distribution functions. So for example, this is somewhat a normal distribution. And you can see that the mean here is somewhere around here, and it can be expressed by expectation of x. X is a random variable of this distribution. Now, if you want to see how spread out this distribution is with respect to the mean, you need to get the variance. And variance is supposed to be expectation of x squared. I mean, it's not the formula for the variance. The formula is expectation of x squared minus expectation of x whole square. But basically what I'm trying to say is you require ex square to calculate the variance. Similarly, if you want to see how skewed your distribution is, for example, this distribution is right skewed. Now, obviously, a distribution can be more right skewed compared to another distribution, or it can be left skewed. If you want to measure that, you need this term, ex cube. Finally, if you want to measure the fatness of tail, for example, this tail here is not fat, but this tail right here, these tails are pretty fat. If you want to measure that, you need to measure kurtosis, which is dependent on e x to the power 4. You can go to higher order of expectation and you can measure different things as well. The point that I'm trying to make is all these expectations of different orders of random variable help to uniquely identify a probability distribution. Now, what is a moment and how does moment generating function actually relate to these things? So, the first moment is called ex, the second moment is called ex square, and the nth moment is called ex to the power n. So, this is the definition of moment, basically. So now that we know what is the definition of moment, we need to know what is the moment generating function. So moment generating function is a function that helps us to generate the moment very easily. It is a closed form function. So let us actually see the formula for generating the moment generating function. So this is mxt. This is the function. This is the function that we will use to generate the moment. You can see that x is the random variable of our original EMF or PDF, and this t is a new variable introduced. So this particular moment generating function is defined as expectation of e to the power t of x, tx. So you may be wondering why. I will answer that later on, but let's first look at the formula and how to calculate it. So we know that expectation of e to the power tx will look like this. So all possible values of x, e to the power tx into the probability mass function. This is for the discrete case. This is something we discussed in the introductory lecture in part 1 of the video series. And also for continuous case, it will be an integral of from minus infinity to infinity. And fx is the probability density function for the continuous distribution. So for these two cases, you can calculate your moment generating function just like this. So now that you have the moment generating function mxt, how exactly do you use it to generate the nth moment? It is very easy. In order to generate the first moment, you take the first derivative of mx and you equate this t variable to 0. For second moment, you do second derivative and equate to 0. For nth moment, you do the nth derivative and equate to 0. That is how easy it is. Now, before I tell you exactly why this is true, why like taking derivative, taking the nth derivative and equating to 0 gives you the nth moment, I will show you an example of how to actually generate the moment generating function and generate moments using the moment generating function. I will first talk about that, give you an example, give you two examples actually, and then I will go back to the reasoning. Okay, so let's dive in. So first of all, let's give an example of a discrete case, which is stemmed from the Poisson distribution. Now, understand that if you're not familiar with Poisson distribution, I have a video on this as well. I will give the link in the description so you can check out that video. But basically, Poisson distribution is a discrete distribution. The probability mass function looks like this. Lambda is the rate parameter and x is the random variable. And this random variable x can take values such as 0, 1, 2 up to infinity. Okay, fine. Now, we know that the mean, that the mean of these PMF or the probability mass function is nothing but lambda. But let's try to now generate this mean lambda using the moment generating function. So first of all, let's produce the moment generating function mxt, which is this. And for discrete case, we know that this will be the formula, and x can take values from 0 to infinity. So that is why we are taking the sum from 0 to infinity. Fine. Now we can replace this PMF by the formula. We can take e to the power minus lambda outside because it doesn't have any x inside it. And then we can write this entire thing like this. Why? Remember that, let's just assume that lambda e to the power t, right? Lambda e to the power t is nothing but y. Let's assume that this is y. That means this entire series can be expanded like this: 1 plus y by 1 factorial plus y square by 2 factorial plus y square by 3 factorial, and so on and so forth up to infinity. And this is a Taylor series of e to the power y, right? This is a Taylor series of e to the power y. Now, if you simply substitute y by lambda e to the power t, you are going to get e to the power lambda e to the power t instead of e to the power y. That is why we could write this entire thing as e to the power lambda e to the power t. Let's just simplify this as this. Since there are two e's right here, it's very complicated to see. So we replace by exp. We just write exp in terms of e to the power e to the power. So we write exp here, and then we put the rest of the things right here. Okay, so we now have mxt. Now let's take the first moment. In order to generate the first moment, we need to take the first derivative with respect to t. And if we do that, we get this. Now we can take t equal to 0. And if we do that, we are going to get lambda. Voila, we have generated the mean, which is the first moment successfully. Okay, fine. This is a discrete case. Now let's look at a continuous case example. So that example we can see of standard normal distribution, and also if you don't know what a standard normal distribution looks like, you can check out my video on normal distribution. I will leave the link in the description. This is the PDF or probability density function of standard normal distribution, which looks something like this. And the random variable x can be anything from minus infinity to plus infinity. We can generate the moment generating function mxt like this. This is the formula for the moment generating function mxt for continuous case. We can replace the PDF by this formula right here. We can take out 1 by root 2 pi right here, and we can just rewrite these two things together like this. Now, here is the interesting thing. This thing right here, which is inside, we can sort of do some algebraic modification and turn it into this. And now you can break this thing up and you can check out the formula for this, that it will actually result to this one. Now, finally, you can take this part e to the power t square by 2 outside because it doesn't have any x in it, and you can put this one inside, and you can put the 1 by root 2 pi inside as well. Nothing has changed. I have just taken the terms apart here and there. Now this whole thing here, if you remember correctly, if you know your normal distribution, this is a normal distribution with mean t and standard deviation of 1. So it is a legit PDF, and we are integrating it in its whole range. That means this should equate to 1, right? This is the law of probability. And so this is now 1. And so we now have our mxt. If we now want to get our first moment, we are going to do the derivative, the first derivative of this. And if we do the math, this is what we get. If we now equate to 0, the t, we will get 0. And we know that a standard normal distribution has mean 0 and standard deviation of 1. So we successfully got mean 0. Fine. Now let's answer this question, that why do derivatives of moment generating function help us to get these things? Like why? We have taken this for granted before. So let's see. So this is how the moment generating function looks like. So this is the expectation. So we can sort of break this down. We can break e to the power tx down in a Taylor series. This is the Taylor series. N equal to 0 to infinity tx to the power n by n factorial. This is the Taylor series expansion of e to the power tx. So x is the random variable here. So we can take t and n out and put the expectation on x only. Okay. Now let's expand this. If we expand this up, it looks something like this. You can check it out. It will look something like this, n equal to 0, 1, 2, 3, up until infinity. If we now take the first derivative, this term will go away because it is a constant term. this term will remain 1 by 1 factorial. This will become 2t. This will become 3t square and so on and so forth. If we now equate t to 0, you can see that only this term will remain. Because we are multiplying by 0, t is equal to 0 here, we are multiplying by 0 here, 0 here, 0 here. All these terms will become 0. And finally, we are going to be left with ex. So we have proven that mx derivative of t is equal to the first moment. If you're still not convinced, let's do this one more time. Let's take the second derivative. So if we want to take the second derivative, we are doing a derivative on this one, on the first one. So the constant term will be 0. It will go away. This will become 2 by 2 factorial. This will become 3 into 2 into t by 3 factorial and so on and so forth. If we now again equate this to 0, equate t to 0, only this term will remain, which is ex squared. And all these terms will go away because t is in the multiplicative factor and t is 0 here. So we have successfully proven that the second moment is also being generated by the second derivative. In this way, we can actually prove all the different moments. So this is all about moment generating function, a core concept of probability distribution. So if you like the video, feel free to subscribe and share. And you can donate to our channel through the link in the description. Thank you very much.